Okay, my name is Jun Chen, and I will be present our work about misalignment-robust frequency distribution loss for imaging transformation. To begin, I would like to first explain the tasks that our work focuses on. Image transformation tasks, which requires to train a deep learning model, taking an image as an input and generating a transformed image. Usually, a loss function is employed to calculate the disparity between the output image and the ground truth, and then supervise the model training. Element loss functions such as LPIPS and L-norm is widely used. However, a key limitation of these element-wise loss functions are they are ill-suited for geometry misalignment, since impressible misalignment can trigger significant response to these losses. However, in real-world scenarios, not all image transformation tasks can access perfectly aligned training data, particularly those involving natural distortions, such as single-image super-resolution and image enhancement. To issue this problem, previous research works propose the distribution-based loss functions, such as contextual loss and project distribution loss. These loss functions show promising in mitigating the influence of misalignment data, achieving better perceptual quality in misalignment scenarios. However, these distribution-based loss functions often ignore spatial location, leading to potential structural error in predict results. This is an example of geometry misalignment in the data taken from a training pair of DPED datasets. Please pay attention to the portion highlighted by the red box in the image, here and here. Due to the difference in capturing perspectives, there is a noticeable misalignment between the input image and the ground truth. To issue this challenge, we propose a novel misalignment-robust frequency distribution loss, namely FDL. In our experiments of various transformation tasks with misaligned data, our proposed FDL achieves state-of-the-art performance. We test the misalignment response of different loss functions, as shown in this figure. Existed element losses such as mean square error and LPIPS will respond significantly to subtle misalignment. Even such a subtle misalignment is most invisible for human. In comparison, our proposed FDL shows a robustness to the misalignment. Next, I will introduce our motivation. Our motivation are twofold. First, the discrete for spatial information of distribution-based loss functions may lead to inability of these functions to pretend the structural accuracy of predicted results. These distribution-based loss functions, such as Wasserstein distance. We argue that this problem is because calculating Wasserstein distance and other distribution-based loss function in spatial domain. Calculating spatial domain will only utilize the local information. However, we think utilizing the global information can address this issue. Therefore, we anticipate that calculating Wasserstein distance in the frequency domain could better preserve the structural accuracy of predicted results due to the richer global information presented in the frequency domain. To validate this, we conduct a straightforward toy example. We generate a set of training data containing multiple pairs of one-dimensional signals and their corresponding targets, with each pair of input and target signals have the slightly different values, and we introduce random shifts to the target and the input signals to introduce misalignments within the training pairs. As shown in this figure, we train a simple multilayer perception network to emulate the mapping from the source to the target and optimizing this model using different loss functions, including mean square error, Wasserstein distance in spatial domain, and Wasserstein distance in frequency components. As shown in this figure, This row shows the model trained with aligned data, and this row shows the predicted results of the row trained in misaligned data. In misalignment scenarios, using mean square error as loss functions expect a significant decrease in prediction accuracy compared to the perfectly aligned training data. Meanwhile, calculating the Wasserstein distance in spatial domain will lead to local structural error, as shown in these two figures. However, we discovered that measuring the Wasserstein distance in frequency domain can reduce this problem comparing to calculating it in spatial domain, as shown in these two figures. Our secondary motivation is shown in this page. We found that frequency components, we already know that frequency components of images possesses specific physical meanings, and we show that these frequency components of the image feature are likely to associate with certain image characteristics. As shown in this figure, we have two images denoted as image Q and D. We first extract their corresponding features using a pre-trained encoder. Then we using discrete Fourier transformation to extract the frequency components, including amplitude and phase of the features of image Q and D. Then we combine the amplitude of the image Q and the phase of image D, and transform the mixed spectrum back to the spatial domain. Then the feature with mixed feature frequency components is decoded back into the image domain, generating the result image. As shown in this figure, the result obtained texture-related attributes such as illumination and color of the image Q, which provide the amplitude, and the structure elements such as object shapes and edge of the image D, which provide the phase. We then argue that in the feature domain, the amplitude and the phase component is associated with information related to various characteristics of the image. Therefore, we believe that incorporating the information in those frequency components in the loss function allows for a comprehensive consideration of the various characteristics within image, thereby enhancing the overall quality of the predicted results. Here shows the framework of proposed method. We first extract image features using a pre-trained network such as VGG, and calculating the sliced Wasserstein distance between the image feature phases and amplitudes respectively. SWD is an approximation of Wasserstein distance, because Wasserstein distance do not obtain a closed-formed solution in high-dimensional space. When used FDL for image transfer, we use the proposed FDL as the style loss, and the SWD between the feature phases as the content loss, because the phase of feature is more likely to correlate with content-related information. These two tables show the performance comparison on real-world image transformation datasets, including DPED dataset and real-world SISR datasets. We use two popular models, CNN-based NavNet and Transformer-based SwingIR, to show the robustness of FDL to different model architectures. As can be seen, the FDL achieves consistent great performance, making a large performance boost compared to previous methods. Here shows the quantitative results on DPED dataset. Compared loss functions will lead to artifact in predicted results, as shown here. While our proposed FDL can generate clear image with natural texture. To further validate the robustness of our method to significant misalignment, we elevate our method using synthetic misaligned dataset. Specifically, for images in DIV2K dataset, we sample two sub-areas from the image. The distance between those sub-areas is randomly chosen, and the biggest possible distance is up to 24 pixels. And we train a SISR model using the synthetic misaligned DIV2K dataset. The result is shown in this table. Proposed FDL achieves much better performance than previous losses in significant misaligned situation. Here is a quantitative result on synthetic misaligned DIV2K dataset. Our proposed method could generate the result with correct structure and no any artifacts. Here is the ablation experiment of FDL, as shown in this table. Calculating the Celeste-Wasserstein distance between frequency components of image features has a significant better performance than calculate SWD in spatial domain of image features. Well, this result is in line with the observation of our one-dimensional POE experiment. And this figure shows the ablation study on the weight of the phase branch, as here the lambda, and the feature extraction backbone. We found that VGG19 achieves the best performance, and the weight of the phase branch might have an impact on the performance, but on the range of the 0.1 to 100, while FDL consistently shows the SOTA performance, shows the robustness of FDL to this hyperparameter. Finally, we show the quantitative results on style transfer. In compared methods, FDL is the only method that can effectively capture the structural information presented in the style image. Pay attention to the first row. FDL successfully captures structure style of the block row, making the stylized face picture like a painting on this wall. This is all of our presentation. Thanks for listening. Our code is already released on the GitHub. You can get them in this link. Thank you.